Okay, welcome everybody to this second in the fall series of TCIPG seminar series on technologies for a resilient power grid. I'm really pleased today to be able to introduce one of our own faculty members who's giving a talk. This is David Nicol, and David's going to talk on simulation and emulation in smart grid assessment. This builds on theoretical work that David's been doing for a decade, and it builds on a lot of very practical work that's going on in the TCIPG testbed right now. Before I ask David to come up, I'll tell you a little bit about him. David is the Franklin H. Woolidge Professor of Electrical and Computer Engineering. That's a new chaired professor appointment. We're really happy to see David in that role. He's also the director of the Information Trust Institute. The Information Trust Institute is the organization at Illinois here that fosters work in security in many areas, including TCIPG, but also including healthcare and aerospace, science of security, and other areas. He previously held faculty positions at College of William and Mary and at Dartmouth College. His research interests include high-performance computing, simulation, modeling analysis, and computer security. He's the author of a widely used textbook on simulation that you might have seen called Discrete Event Systems Simulation, and he was the inaugural awardee of a new award that ACM gives out each year for his contributions called the Simulation Distinguished Contributions Award for his contributions in research, teaching, and service in the field of simulation. So without further ado, please welcome David Nicol. David, we look forward to your presentation.
Thanks, Bill. You can do all my introductions from now on. That'll work for me. So life sometimes has these defining moments where it takes a pivot. And one of those defining moments happened to me in the summer of 1999 when I got a phone call from the assistant to the provost at Dartmouth College. And the assistant to the provost wanted to know whether it would be convenient for me to meet with the provost in 1 hour, a question to which there's exactly one right answer, even if you were dressed as a computer science faculty member in the summertime often is. I won't go through the rest of the story, but what happened as a result of that phone call was a redirection in my career, because before that time I had been doing only work on modeling and simulation of high performance networks, large networks, and the phone call led to the imperative that I start applying some of that stuff in security. Well, one thing led to another, and some 13 years later, here I am standing in front of you to talk about still simulation and emulation, because when I made that change, I brought my toolbox along with me, and I brought my way of thinking along with me as well. So 13 years later, I stand here before you, a modeling and simulation guy with a dream. I have a dream. The dream I have is that one day we'll have the capability to embed a large, complex smart grid subsystem within a high-fidelity virtual environment and do quantitative assessment of things like behavior under realistic conditions, reliability in the face of faults, effectiveness of security measures that we are deploying in said subsystem, and even the presence of unknown vulnerabilities. To achieve this dream, there's something critical that's needed, and the critical thing that's needed is a high-fidelity virtual environment. So, I have another dream. The other dream I have is that this foundational research that has to happen to pull all these other things off can actually be used. It's not just that I graduate students and publish papers and the usual academic thing, but that this gets used in a way that is beneficial to others, that it gets embedded in a smart grid assessment facility where a user could come to this facility, remotely even, where it requests hardware and software, has an experiment in mind, describes what that experiment is, submits it to the facility. That facility is managing multiple of these systems. If you've ever interacted with a supercomputing center that's managing, the facility of all the computers that it has, something like that. When it's the turn for the experiment, then the resources that are needed for that experiment will be allocated, configured automatically, and checkpointed so that you can go back to that point again. The experiments run according to the experimental design. The output is stored. The resources are released and users are notified. And if it's really smart, have some kind of automation that looks at what the experiment was trying to achieve and what the experiment actually achieved, and then suggests additional experiments to the users. So those are my dreams. Now, to realize this dream, we have to have virtualization and adaptive configuration, because to do all this business of swapping in resources and managing them and releasing them and doing something else again, that all relies on these particular things. And so simulation and emulation is a key part of this. Virtualization and adaptive configuration are part of this as well. So there are many pieces of the puzzle to be drawn into this dreamland I have. Some of the pieces of the puzzle are devices, relays and phasor measurement units and collectors of data from phasor measurement units and programmable logic arrays and meters and sensors and AMI readers and things that you plug into the wall to measure what is happening electrically, and inverters and firewalls and data acquisition devices and gigabit firewalls. There are software systems that are part of this puzzle. Data historians and control systems and energy management systems and display systems and visualization systems and things that you can use to do online analysis and other intrusion detection systems and meter data management systems. There are simulators. Did I mention that we're interested in simulation? There are simulators here. We have electric flow simulators that are of interest. Commercial ones by our friends at PowerWorld, by folks at RTDS, or that's the product that they have. I'll say more about that. There are other commercial electrical flow simulators as well that have to be involved here. Communication simulators, some of which we've developed here, some of which are developed by friends and students, some of which people know about, but we're not using, not enough cycles in the day. Things like NS3 and OpNet, well-known communication simulators, and simulators for AMI like the Itron test bench. Other pieces of the puzzle, analysis tools, hardware and software listed like there. So, all these pieces of the puzzle, we got a lot of it. Oh boy, do we got a lot of it. We got pictures. Thanks very much, Tim Yardley, for taking these pictures. We have racks, and those of you that are in the field will recognize the Schweitzer blue. Lots of Schweitzer stuff in these racks, lots of banks of computers that we use for our virtualization. There's our RTDS and our RTDS expert. The RTDS is a hardware-assisted electrical flow simulator. It uses FPGAs to make things go fast. Very, very capable piece of equipment. Very, very nice way to generate very realistic electrical flow characteristics that can then be presented to the devices in our system. Here's a rack of servers that we have to run emulations. Here's a device that we use to look at electrical waveforms. Here's a solar array. Here's the backplane that's got the National Instruments lab bench on it. Here's a device, a meter that one of our people took apart and put it in some hardware intrusion detection system on it. Here we have other things you may recognize. Again, some more Schweitzer gear. Here's something that's called Mu Dynamics, which is a piece of gear one uses to fuzz test equipment. You shoot a lot of traffic at it that's noisy and see if it topples over, and then understand why it is that topples over. Here's a relay from an AMI system, and here's a whole bunch of meters. We've got lots and lots and lots of pieces to this puzzle. I have a dream. And the dream is to make this pile of pieces, the sum of the parts, have a whole that's greater than the sum of the parts. Pull this all together in some coherent way and actually use it in useful way. So, we need an infrastructure that includes all this reality, but we also need the infrastructure to include models of real stuff. Because when we're modeling, when we're trying to analyze great big subsystems, what we can stick in a lab is a lot smaller than what's out in the field. And so the way you represent things that you can't have for real in the lab, that's where you bring in the simulation and the emulation. And that's really the point of this talk. So to assemble this puzzle, we need to present to every component in it at its interfaces realistic representations of the environment that it's expecting. So when you've got a device that's looking at electricity, you need to present something to it that looks like electricity. When you have a device that's expecting to communicate using some funky communication protocol, then it needs to be talking that communication protocol either to another real device or to a simulated device or an emulated device. The point is you have these components, they're interacting with each other, they're interacting and they're observing the environment. You need to present to the devices and all of their sensory inputs things that look like what they expect to see out in the field. So the pieces of this particular ensemble we have, I'm told to, there we go, we have the electrical flow simulator here. That's going to distribute electrical state to specialized devices. Those would be your relays and your PMUs and these things that our vendors so kindly give us to put in our lab and to use and evaluate. In addition to the specialized devices, we would have also not so specialized devices, but real nevertheless, human-machine interfaces. These would be consoles where operators might sit. So that's the real stuff. In addition to the real stuff, we'd have emulated stuff. And I'll talk a little bit more about the difference between real stuff and emulated stuff. But basically, emulated stuff, you're running real software, but in a container that makes the real software think it's running on hardware that it's not really running on, or running on software that it's not really running on. But in any case, it's emulation. That's part of this puzzle as well, and you need to be able to have emulated pieces interacting with the real things. Then you have also the simulated pieces of the puzzle. All of these things, emulated, simulated, real, they all have to be brought together. And on the device side, they're going to be brought together by the communication simulator as well. Not only does the communication simulator serve to model the infrastructure that's used to facilitate the communication between the devices, it's actually the glue that's holding all of those devices together in this system. So, emulation is executing native software to produce some kind of behavior. Simulation is executing models of software to produce behavior. So if you're actually executing the software, you're going to have, if your inputs have high fidelity, then the behavior is going to have high fidelity. So you have high fidelity functional behavior. Typically, what happens when you emulate something is that that behavior is tied to wall clock time, and we'll say more about this, and we'll see more about this shortly. But basically, you're running the software, and the amount of time it takes to run that software, that's how some scaled version of that is what you presume it took to run that in the system that you are emulating. It tends to be resource intensive because you have big chunks of software. Each of them are taking a piece of memory. Each of them uses all of the resources that it would take out in the field. There's no shortcuts taken. And so if you're emulating many hosts, then you're going to have many hosts on which to run the emulators. And so you have resource-intensive requirements there. The good side is that it doesn't take that much effort to take a piece of software and emulate it. You're not changing the software, at least you shouldn't have to, or if you do have to, you do that in an automated sort of way. To be contrasted with simulation. In simulation, you're using abstraction to accelerate the changes to the model state. In emulation, you run the software to change the memory values, the register values, and so on. That's the model state. And with simulation, you're using abstractions. The model state is smaller. The computations that you use generally are faster as well, which means that when you run simulations, then it's not tied to the wall clock time. It may be running faster, it may be running slower than the wall clock time. There's sort of an inherent speed at which these things will run, and you let the requirements of the simulation dictate how fast it will actually run. The memory that's needed to run these is typically lower, but the downside is that if you want to have a simulation of a TCP protocol, then you have to write a model of the TCP protocol. And there is some complexity there, and that's just the beginning. And so that's one of the aspects of simulation, is there's a lot of work to develop the models that you would include in your simulations. Think about the difference between emulations and native execution. Again, emulations run software in virtual machines. Many of you use, or at least know of, something like VMware, so if you are a Mac user, you can have VMware on your machine, and then you can run Windows images on that. And so it looks like Windows is running on your Mac. And all practical purposes, Windows is running on your Mac. But it's not running on a Windows machine. It's running on your Mac. So there is this shell around it. There is this layer, this virtual machine that's supporting all of that. And what's happening there is that resources are being shared among multiple virtual machines, usually, transparently. So there is some line in the protocol stack or in the application stack, and below that line, the virtual machine is going to take care of it, and above that line, you're going to be running some application code. And you can draw that line in different places. So-called lightweight emulators will draw the line high. There will be an operating system, Linux, that's shared by all of the virtual machines. So when any one of the virtual machines calls an operating system function, or accesses some operating system state, it goes down into that one common shared copy of the operating system. That's relatively high. But it means that the virtual machines can be relatively lightweight. You can push that layer, that boundary, lower. You can push it so that every one of these virtual machines has its own version of the operating system. Well, now new possibilities open up. You can have within one virtual machine management system, you can have one VM running Windows, another VM's running Mac, another one running Linux, and so on and so forth, because each of them carries their own operating system. Where is the line being drawn? The line being drawn now at the hardware. You're running, say, x86 images on an x86 machine, and there's a shim of code between the application and operating system that's running and the actual CPU that's running as well. But just in case that's not clever enough or sophisticated enough for you, or just in case what you have is software that runs on an ARM processor, but your emulator runs on an x86 processor, now you push that layer even lower, and what you need now is a translator that's going to be interpreting the ARM code, the ARM binary, and execute that on an x86. So the lower the bar, the lower that threshold, the closer it is to the hardware, the more work is involved in all of this. Okay. So some things emulators aren't particularly well suited to do, particularly in this space we inhabit. And that's when the processor, when the machine that you want to include in your experiment has some kind of specialized gear on it, like some sort of signal processor, right? Because if you have a hardware signal processor, special chip that's on that machine, now you're not going to find in any stock emulator, you're not going to find support for that. If you want to emulate that, you're going to have to write that yourself. And so when you bump into these special pieces of hardware, or hardware that has special chips on it, then more than likely you're going to have to run that natively and not run that through emulation. Other critical differences: the native execution is tied to the wall clock. I mean, really, really tied to the wall clock. You got the box, you run it. How long did it take? You look at the wall clock. That's how long it takes. When you have an emulated machine, that it's running in real time, and normally when you ask it what time it is, the time it's going to give you is real time. But we will see that there are ways that we will want to change that, and reasons for changing that. The interface to an emulated piece of software is usually just through networking, because you have a virtual machine manager, and there's a standard there. The interface with a device that's actually running natively is particular and peculiar to that particular device. So those are key differences between emulation and native execution. If we're going to achieve this picture where we're integrating all sorts of things, we're going to have to interface somehow the electrical and communication simulators. So I can draw this picture, and in this picture it looks as though the electrical flow simulator is pushing electrical state to the specialized real devices, to the emulated devices and the simulated devices. But that ain't what really happens in the lab. What really happens in the lab, and we've done this, is that the electrical flow simulator state gets pushed onto a database. And there's a server. And that server will push out the electrical state to the real devices because they have to see it in ways that they understand. and not over some communication network. And there'll be an interface with the communication network, and that interface to the communication network will be the liaison between the devices, the emulated devices and the simulated devices, and all that electrical state. And so that interface will reach out to the state server and get the state and push it out to the simulated devices or the emulated devices, or they will reach back and they will ask for it, one way or the other. The key thing here is that we have to have this piece. Now, those of you that are still awake will leap to the observation that the flow here of influence is one directional. That you have electrical state can affect the devices that are in the communication simulator, but suppose something changes in the communications in the simulated side. And we have done simulations where this has happened. We have done experiments or demonstrations where someone in the HMI, a hacker, got into a relay, changed the setting on it, which caused a line to open, which caused the flow topology to change, which should change what's happening over in the electrical flow simulator. Which means that on the simulation side, you can be doing things that affect the electrical flow side. Now, for most of the flow simulators that we have right now, we haven't sussed out how to connect that particular backfeed. Back in the day, we had a version of PowerWorld, and we had friends from PowerWorld who were graduate students and now work at PowerWorld, and they were able to pry open the cover on that and allow us a means by which we could affect the topology, the flow topology inside of PowerWorld, and have changes on this side, affect changes on that side. We don't have that power right now, so that's a problem area for us. We have the challenge of being able to integrate these physical devices into this ensemble in a configurable sort of way. And so one question would be, how do you make a relay or some other device think it's out in the field? We'll use relay as a particular example because this is something that's actually done. A relay out in the field is going to be looking at current at levels that you're not going to find in the lab. So recognizing this, then the manufacturers of relays have as an interface to the relay that you can have it be looking at voltage, which can be high but not have high current, and have it react to voltage in the same way that it would react to current, and then allow us to, or allow a user to present voltage to that relay in the lab in ways that make it act as though it were out in the field. And a device that allows one to do that, something that's called an adaptive multi-channel source, and that's something that you can interface, you can program. You can stick things in there and you can send commands to it. And so through this means, we can take electrical state somehow and get some encoding of it to the, all sorts of things are happening, get some encoding of it to the adaptive multi-channel source and then have it present to the relay. And so that's how we make the connection between the relay and this electrical state. We have an issue of multiplexing the inputs or demultiplexing the outputs of some analog device. If you're going to have it in a lab situation, you're going to want to use it, have it connect to some things in one experiment and other things to another experiment. I am told by my lab guys that there are things that we could purchase to do something like this. This would just be a bus, just be a switch, a hardware switch that would allow us to switch these analog inputs and their outputs. So this is a solvable problem, but I want to emphasize it's not something that we are prepared to do in the lab just yet. Integrating the RTDS, again, this was a hardware-assisted electrical simulator, into this ensemble has its own challenges. The RTDS, you interface with it through a special program that is called the RSCAD. Through the RSCAD, an operator can select configurations for a special card that we have, which is called the GTNet. And in the GTNet, you can have the RTDS produce outputs from particular protocols. It can look like it's speaking DMP3. It can look like it's PMU, a number of things that you can have the GTNet do. And through the RSCAD, you can tell the RTDS, I want it to be thinking, I want to be speaking DNP3 on this particular experiment. Through the RSCAD, you load models, the particular topology and parameters of the models that you want to run, and during runtime, you can interact with the RTDS machine through this particular program. Well, to make it usable to us in this kind of configurable sort of way, our lab guys wrote a shim. We call it RSCAD streamer, and the RSCAD streamer then allows one to interact with the RTDS in programmable ways using the experiment setup commands through the RSCAD streamer to the RSCAD to the RTDS. So this is all working. I want to talk now about issues in integrating emulation and simulation. I keep talking about the importance of time and wall clock time and virtual time. Here's the deal. An ordinary emulator is embedded in real time. You have a software stack, it's running in the process on a virtual machine manager, and if it asks what time it is, it's going to go to a hardware clock, and the hardware clock is not on the machine that's being emulated, but is on the machine that's executing the emulation. I'll have graphics that will illustrate this in just a moment. That's not good enough when you're going to take an emulator and have it interact with a simulator. This interaction needs to be managed very carefully. And some of the work that we have done shows how to take a lightweight emulator and embed it in virtual time so that it will solve this particular problem. So that when virtual machines in this system ask what time it is, when virtual machines in the system put a timestamp on something, the timestamp is a virtual timestamp that comes from our management of virtual time and not a hardware timestamp that comes from the machine on which the virtual machine is executing. So why is this needed? I'll give you an example of why that I should hope motivates why this is needed. So just imagine, thought experiment. You have a bunch of emulated devices, and they're all operating in synchrony for some reason in the real system, that within some small period of time, they all generate a message and send it out. All right, and we'll just say that time is 1,000. If all of these VMs are running on a virtual machine manager that's one CPU, it's going to be running them serially. It's going to say, VM1, why don't you run for 10 milliseconds? So it'll run for 10 milliseconds, and it'll produce a message, and the timestamp on that message, or the time at which that message pops out, is 1,000. All right? So now it goes to the next VM. It says, next VM, it's your turn. So it takes its slice. Time goes by. A message comes out. At what time? Well, it comes in this particular animation 1,000 time units later. And then the next one has its chance. Another 1,000 time units go by. The next one has its chance, and so on and so forth. And what that means is if you were to capture this traffic and present it to a network simulator, what does that network simulator see? What it sees is this dribbling of packets. Here's one at time 1,000, here's one at time 2,000, here's one, and so on. And it's this gap between them. Where did the gap come from? The gap came from the execution of the emulations on this machine. The gap came from the fact that one machine was multiplexing itself between the executions of these various VMs. So why should that matter? Suppose this network simulator is one where the medium is shared access. What happens in a network when a whole bunch of packets show up all at once and say, I want this medium which is shared by everybody now? Well, there are protocols for detecting that there are collisions and backoffs, and there's some kind of serialization that the protocol will do. But that's what's not is going to happen in this naive way of using the timestamps from the virtual machine. Or suppose that you had all of these packets were arriving at one particular switch and were leaving through the same port. In the system where the emulator is not embedded in virtual time, you'll have a packet. It'll have all kinds of time to go through the switch. The next packet will come along and have all kinds of time to go through the switch, and so on. Whereas in the real system, they all arrive at once. Boom, it's a burst. That means the queue is going to all of a sudden have a bunch of packets on them. If the queue's not large enough, you're going to lose some. You see, the behavior in the network simulator depends very much on the timestamps that you put on these packets that come out of the emulator. So we need to solve that somehow. When we have solved it, and embed the emulator in virtual time, then the timestamps on the messages that come out are closer to reality. So the virtual timestamps on the messages are closer to reality. Here in our animation again, the time at which the first message comes out is again 1,000. The virtual time, we can say, is 1,000. The time at which the second message comes out is 2,000, but the virtual time is 1,000 because we have tinkered with the management of these VMs so that they have access to virtual time, and the timestamps that are on these are virtual, not real. And so we can then present to the simulator this batch of packets that arrive all at once in virtual time, even though physically they're still dribbling out of the emulator, which means that we have to manage this interaction between the emulator and the simulator so that we can get the virtual times right, that for a given slice of time, we can get all of the traffic that's going to come out of the emulator and present it to the simulator. And so that's what we have to do, and that's what we have done. And so some of that is making sure that no traffic is lost. Some of that is managing the fact that there are inherent errors in these timestamps, in these virtual timestamps that come out of the emulators, even though we're doing this virtual time management. And that comes from the fact that, at least in the virtual machine manager that we've tinkered with, that once you allocate to a virtual machine a certain period of time, a millisecond, 10 milliseconds to run, then there's no stopping it. There's no saying, oh, stop, I got a message for you. You give it a time slice, and it is numb to the world for that time slice. And that numbness during that period is cause for some kind of temporal errors. So we manage that by the time slice size, and we have analyzed that to bound what the impact of that particular error is. We also have to be careful about exploiting parallelism here, and that's something else that happens in this piece that manages virtual time between emulations and network simulations. So now let's look at some challenges, some problems that arise in the space of network simulation by virtue of the fact that we are trying to model smart grid systems. So when you simulate wired networks, there are a variety of standard and also specialized protocols that systems that you model may need. That would be things like 61850, TCP/IP, DMP3, DLMS COSM. There are routing protocols. On the wireless side, you're going to have some model of the physical channel, the radio channel. If you're going to determine whether when a message is sent out on the radio channel, it is received or not. You're going to have to specialize protocols that come from the domain, including C1222, Zigbee, the ubiquitous 802.11, and others. You're going to have to deal with mesh architectures. The point here is that to support this is a lot of work, and to develop a library of models for all these things. That's why a company like OpNet stays in business. It's because what they sell are libraries of already defined, developed, and tested protocols. And so if you've got a big enough checkbook, you can sit down and you can throw together a model that has complex protocols pretty quickly. You don't have to develop them yourself. If you're an academic, then you get to write them yourself. Or if you're the graduate student of an academic, then you get to write them. Let's be clear on who's doing what here. There's some research problems. At times, these ensembles that we have of real devices, emulated devices, and simulated devices have to run in real time. When and why? When we have those real devices. When we plunk down a real PMU that's listening to a real GPS signal, then there is only one option that we have for running anything along with that, and that's to run them in real time as well, unless we want to get into the business of putting the time signal in virtual time as well, which might be something to do, but that's just one example. That's in real time. So if that device in the ensemble is running in real time, that means everything else that interacts with it is going to have to run in real time as well, in particular the network simulator, which means that we are motivated to keep up with this real time by looking at the way that we model and execute these network simulations to go faster than they would if you just did them naively. And naively would just be one packet. If there's a packet in the real network, then there's a packet in the simulated network, and that just won't get you there. So what we're about in this thread of work is to try and reduce the computational cost and still have the fidelity of behavior that you need in the network. One of the things about networks in the smart grid that we can take advantage of is a lot of the traffic is very structured. A lot of the traffic is periodic. And what that means is that it gives us opportunities to represent some of the traffic that we're really not very interested in, background traffic, except for the impact that it has on the network resources, except for the fact that the background traffic is chewing up bandwidth that something you are interested in your experiment needs. And so what you need to do there is to try and be efficient in simulating the background traffic so that it's reflecting what the background traffic in the real system would require, but focusing your computational attention on the foreground traffic. So that's a fine idea, and we've been exploring that for a while and have shown that you can get 3 or 4 orders of magnitude of speed up in large network models by doing exactly that. But it does mean that in this simulation model, where you have some abstract versions of traffic floating around with some detailed versions of traffic floating around, all at the same time and sometimes all in the same place, you have mixed levels of abstraction that have to be represented and managed in your model. So here's an example right here. You can imagine you prop open the cover of a switch and look at one of the output ports. As packets come to the switch and are routed to that output port, then if that output port is busy, then they queue up. All right, so now if you have a lot of business going on, you have real packets queuing up for processing by that output port. But you could have these higher level abstractions, these flow abstractions, and they're all trying to get out the same output port. And so somehow this model of the switch has got to account for the fact that in the model you have different representations of traffic, and its behavior has to be defined in terms of those different representations of traffic. Now, one of the things that we have learned in this business is that the first thing that you think of in doing the flow abstraction isn't right. Because the first thing that you think of in the flow abstractions is going to lack something that's really important when you're trying to accurately capture the behavior of traffic in a network. And what it misses is burstiness in a flow. So somehow, in the naive way, you're not going to have, we'll call it variance, you can call it burstiness, call it what you will, but one thing that we have learned that in the flow abstraction here, we have to characterize how bursty this abstracted flow is and then work that burstiness into our evaluation of this switch right here. That's another talk. I just want to alert you to the fact that that is an interesting and hard problem. So, more research problems for modeling smart grid networks. What I talked about just now was how to make background traffic faster and some of the issues there. What I talk about now is how to make the simulation of foreground traffic faster. So the observation here, 2 of them really, one of them is written down and one of them I'll just tell you, that a real switch in a network runs managing the competition for its resources fairly complex algorithms. And because it executes fairly complex algorithms, a first order naive, I'm going to model this switch kind of approach is either going to ignore those details and have behavior that's not reflective of reality, or pay attention to those details and consume a lot of CPU cycles just for the purposes of getting a packet through a switch. Those are the options. So the observation we make here is that the time scale involved with a packet going through a switch is measured in microseconds. The time scale of the applications that are generating and receiving the traffic is measured in milliseconds. So you might say to yourself, why should I get all bent out of shape down in the network simulation of whether I have the latency part of the packet's traversal through the switch exactly right? Right? With a difference. And the difference is that you need to have the average latency right. If you get the average latency wrong, then you can screw up throughput through formulas for TCP, but I won't go there. But let's just say, if we can manage this simulation so we get the average latency right, then that, but not the individual latencies, that'd be a good thing. But notice that if you have a packet that's lost inside of a network, I don't care what time scale you're at. If that packet is being managed by TCP, that means that the applications are going to change their behavior. They're going to engage in the TCP protocol to do that. All of this is to say that we come to this and say, look, what we want to do is develop a model of whether a packet survives passage through a switch and how long it passes through that switch in such a way that the chance that the packet is lost is accurately captured. We're not so concerned about how long it takes that packet to go across that switch, so long as the average is right, in such a way that when the packet arrives at the switch, we can decide whether it stays and how long it's going to go spend in the switch, and then off it goes. So we can all do it in one calculation, one event. Whereas with these complicated protocols, your packet comes in, you thump around in the memory, you're calculating this, you're calculating that, all sorts of work's involved in getting packets out, where what we want to do is make this fast. Packet shows up, make a decision. Did you live? Did you die? If you lived, how long were you in this switch? Goodbye. And then push it right along. You have to go to the mic.
So can I ask a question?
Well, the boss just told you could.
Boss said yes?
The boss said yes.
Okay. Well, it's sort of related to some of the things that you were saying, and maybe my question is maybe a little naive, but let me ask it anyway. You said to speed up, you have to really have these abstractions and to speed up the simulations. And now you are looking at seemingly real packets going through the network. So I'm just wondering, when you're looking at this network behavior and you have abstractions and now you want to look at the real packets and perhaps do some inspection, I'm not sure. How do these two reconcile? You know, do you have
I want
different
everybody to note or take on my oath, I did not pay Ravi to ask that question at this time when I'm showing this slide. Okay? You can sit down now, Ravi.
Exactly right.
All right.
I mean, the slide doesn't make...
No, I was going to talk to it, you know, and but really and truly, this does. All right. So I won't go into all of the details of what this graph describes, except that this graph up here, this bit right here that says real, that's the real thing. That's a switch in the lab. That's been instrumented in various ways, and we're looking at the time through the switch as a function of the packet number in a sequence, and we have two flows. One's very fast, one's not so slow, and this is telling how long it takes to get through the switch and whether the packet was dropped. And this is the real enchilada. Then we say, okay, we've got this way of simulating. We have this protocol that we discovered this switch was operating on. And so now we do a detailed simulation of that. All right, a lot of work. This is what we're trying to avoid. And now we can compare these two things and say, well, this is how that same set of packets behaves when we're doing the simulation. And here's our tricks. Here's the thing that's down here. So this is when we are doing very fast calculations of latency. And what we see is, you know, qualitatively and fairly well quantitatively, oh, there it went, we're talking about the same thing. We're getting the same kind of behavior. So it's an excellent question, Ravi, and it's because it's an excellent question that we addressed it. And this shows you that this is something worth looking at. Okay, moving right along.
What's the underlying reason?
So what is the underlying reason?
Why is it that you're getting...
Oh, okay, I can do that. So the trick is to manage your model, your data structures inside of your model, so that even though you have shunted the packet out and caused it to go along, you still remember it, and you're calculating when it would actually have left. And so there's this kind of this feedback, and you can use that information to sort of make corrections as you observe mistakes. And that's it. So you lie, and then you try and fix it. So wireless networks have their own set of challenges, but one that's widely recognized through all sorts of places is that an accurate high-fidelity model of a wireless channel is going to take a lot of complication. Now, the motivation for us to look at this is that as wireless makes its way into the smart grid, into subsystems or mesh networks or what have you, that there are complicated interference geometries that are going to have to be accounted for somehow in your wireless model. When you have obstacles, that affects the radio beams, that affects whether or not messages are received or what the signal strength are when they are received. And the fact that wireless is being used in the smart grid in places where they have these complicated geometries is the question of interest to us. So here's a graphic that suggests that there's a range of models for wireless for the radio channel that vary in their computational cost and fidelity. And off at one end, you have something that's free space. Basically, you measure the distance, and then you take 1 over the distance squared, and that's how much the signal degrades, the same as gravity. Sometimes you get really fancy, and you degrade it by a power that's a little higher than 2 and stick another coefficient on there. There's something else that is not exactly free space. It allows for a second ray that's sort of reflecting off of the ground, and you combine those two. The point here is that these are statistical models. They do not take into consideration precise obstacles that are in the way. They're very fast, but it's hard to find the parameters that are going to make them accurate in any given context. So you go over into the domain-aware area, and now you have things that are ray tracing, which is sort of how ray tracing goes in graphics, where you can do something like that. Imagine shooting radio beams all over and having them bounce here, there, and everywhere, and gather up how much signal energy you get at a receiver. And you can get a little fancier than that and use something that's called translation mine, which ought to appeal to electrical engineers. But it's some equations that come from transition lines. You have a model of electrical transference that uses that. That's a little more work and is a little more accurate. And then if you're really crazy, then you could do it with Maxwell equations. But you don't really want to do that. The point is that you want to find some spot in this space where you get the answers at the level of fidelity that you want, but fast enough. So we've been looking at that. One of the things that we wanted to do was to do some validation of various kinds of radio channel models. So we used the anechoic chamber that we have here at the University of Illinois to set up some experiments to do validation of these various models. And we learned some interesting things from that. One is that if you use ray tracing as a model, you can choose either to consider the phase, the radio energy is going in waves. You either consider the phase or you don't consider the phase, and it turns out that you better consider the phase, otherwise you get some odd behavior that you don't want to have. But even more interesting is that you use these models, but there are parameters that you have to have in the model that you just don't know. Where's the antenna in the black box? What's its shape? What is the beamform coming out of this thing? When a signal hits a wall, how much of it reflects, how much of it passes through? These are parameters that are in the model, but you don't know. And so it turns out, in our estimation, that this, more than anything, is a complicating factor in trying to come up with high-fidelity wireless models, because you're really not doing what it is. You're really not modeling what reality is, because you can't really measure reality in that case. I wanted to hit a couple of case studies and then open it up for some questions. One case study is how we're using this stuff in partnership with some folks that are part of what's called the DEF consortium. DEF stands for Deter-Enabled Federated Testbed. We're in the process of doing a demo for the Department of Homeland Security Security Technologies Conference in November. What we're doing is we're federating the testbed that we have along with the testbed that's at ISI and PNNL. And in the demonstration, we'll show how situational awareness is maintained in network systems. And so this is a picture of what the federated experiment does. And over on our side, we have our RTDS, which has been configured the way that I described, and it's feeding some PMUs and being collected by a data collector, and we're displaying it. And that information out of our data collector is going to a network emulation that's running over on the other side of the country at ISI, where they have a large-scale network topology that they're emulating and managing in emulation using BGP, and then is delivered through that network emulation up to their own data collector. On the P&L side, they're doing something similar to what we're doing, except they're not using an electrical simulator. They're using a wall socket, and then they have some simulated PMUs, which are just generating junk. And, they're generating synthetically created traffic. And that's being developed to the data collector and being shown, and then also sent up to ISI for display. And the point of the exercise is that when we do something down here, we'll model a generator fault and then or a drop, and then that'll show that some waveforms change, and that'll get up here, and that'll pop down there, and they'll see it. So this is really a demonstration that all our plumbing works, but there's a lot of work to get the plumbing working. And this just shows you the kind of directions that one can go with the kind of technology that we're working with.
Excuse me?
Yes, sir.
What are the different locations?
No, you have to go to a microphone.
My question was, can you give us the different location? When you talk Illinois, PNNL, ISI.
Oh, yeah. So Illinois is, look outside. ISI is in Los Angeles, California, and PNNL is in Washington State. Okay? So these network links are going over, wide area networks. So I've been signaled for 10 minutes. I have another case study. Maybe I'll just cut to the chase so we can take some questions. And the chase is that we used this test bed to evaluate a certain attack, DDoS attack that we discovered was possible under the C1222 trace service. I won't go through all of the details of that attack in the interest of allowing some questions. But the point here is we use this facility that we have, a combination of emulation and simulation and wireless simulation, to evaluate the impact on the network as a whole of this attack, and found the alarming conclusion that 5 attackers using this attack could gum up the whole network. You see these down here? This right here, all those red dots, that means gumming up the whole network. And this over here means gumming up the whole network. And so that's a bad thing. And so that says that there's some vulnerability to this particular attack that ought to be looked at, and something ought to be done about it. So to summarize and then open up for questions. So here at TCIPG, we're building the capacity to evaluate complex smart grid systems. Simulation and emulation are at the heart and soul of it, and we're doing this and finding good research problems that are motivated by characteristics of smart grid systems. Of course, you'll see that the solutions that we come up with apply not only in the smart grid context, but in other contexts as well. But we pick the ones that matter here. And with that, I tremble as Bill goes to the mic to ask the zinger he has been waiting.
Thank you, David. Boy, that was a zinger, right? No, I do have one question I think you talked very well about the need for abstraction, the difference between simulation, emulation, real equipment. And that's all on, if you will, the side of the system. Now I'm thinking about in security assessment, which this is being applied for, we need to have perhaps that same kind of hierarchy of abstraction in the models of the attacker and the attacks. And I wondered what your thoughts are on that, and how do you sort of, if you will, translate attacks across levels of abstraction in this system?
There is one place where you have to have detail, and that is when you are trying to, say, discover a vulnerability in software. So when these particular vulnerabilities, let me try again. Vulnerabilities that are present because of implementation, you can do nothing but have the implementation, obviously. All right. You can step back from that, and you can say there are vulnerabilities due to problems in a protocol specification. Now you don't have to have the details for that. If there's a problem in the protocol specification, then you could be managing things at that level of abstraction. You can go at a higher level of abstraction still if you say, I really aren't interested in how it is that this host was compromised. I'm going to presume it is compromised, and now I'm interested in what effects it can have on my model, given that it is now compromised, given that it is root. What can it do? What damage can it do? And there's another kind of analysis that you can do but every stage, the higher you go up in the abstraction, sort of in some sense, the more you have to start to assume or start to say, I'm not really trying to deal with that when I'm trying to deal with something that's appropriate at this particular level of abstraction. So I think it's key, absolutely. Because if all we did were implementations, we wouldn't get anywhere. All right, but it is true for implementations, that's the only way to get there. Yes, sir, Ravi. I'll go to the mic, please, sir.
You have time for one more question?
If you ask it at the mic.
I'll be quick. I think you sort of intrigue me here, and I again, you may all have already done this. Let me give you the fault analogy, right? You have simulations, and then you have to study the impact of faults. The underlying abstractions that you use to study the impact of faults has to be different from the usual simulation. Otherwise, you're already presuming what the fault might or might not do. So, how does that analogy now should transfer to security, for trusts, for not just vulnerabilities, for attacks and their behavior and so on?
In your reliability models, you will undoubtedly have a description of how this system or how this component behaves or can behave as a function of its state. And you would use a fault to push it into one of these states from which certain transitions that are possible after this fault can occur. And we would do exactly the same thing. I'm treating it at a very abstract level, but it's exact. At that level, there's no difference between injecting a fault and injecting a security breach. Now, practically speaking, most faults happen due to some independent, stochastic, all that stuff, and security breaches don't. And so where the challenge there is in doing the analysis of these kinds of models, which at that level look very similar, but what's different is the way that you inject the breaches. In a security model, you can imagine, and you should imagine, particularly in the smart grid case, that what you have are simultaneous security breaches in a bunch of places that are all trying with one common thing to try and cause something bad to happen, because that's the way you make bad things happen. But that's the key difference, I think.
Very good, thanks.
Prosper.
Yeah, Prosper Panompabi from University of Illinois. My first question is, I want to know, do you have any course you are teaching here where, people can come learn about the simulation, emulation, and like a week, I discovered another word, which is a stimulation. So, do you have any class people can come?
It meets at 9:30 on Wednesdays and Fridays in Siebel in room 1304. I will save a space for you in it, and we'll be looking for you
Okay, thanks.
Wednesday.
What do you think about the idea of giving access to our test-bed resources to some smart undergraduate student? The idea is, can we make some democratization of the test-bed resource here?
Can I make some democracy?
Can we allow some undergraduate student to use our test-bed, because it's like too close and there is not too much, interest.
So
no.
there are barriers to using the test bed, a number of barriers to using the test bed. One of them is just knowing what to do.
Yes.
Since people typically don't know what to do, having the information available so that they can learn what to do. And then also having you there to help them, or someone there to help them. All of these things are possible, right? There are some, depending on what equipment's being used, there are some other issues with respect to access. But the broad answer is that as director of IT, I would be delighted to see some excellent undergraduates be doing some research projects that involve the test bed.
Question from online.
So
You have 24 sites.
online, we have a question. Is there any standard definition document or guide for emulation and simulation? And can we define the RTDS as a simulator or emulator?
I would definitely call the RTDS a simulator. I'll tell you the reason why, although the reason why is that it is solving a mathematical model of electrical flow. And so it is not the real thing. I don't know that there's anything there is something corresponding to emulation of electrical system, and that's analog. So analog computing is emulation in I think in that space. But it doesn't wouldn't make sense to me to say that the RTDS is an emulator. Is there a standard definition? I don't know that there's a standard definition. I guess you could check Wikipedia and see what it says. Effectively, that's a standard. My definition, I've tried to explain, is when you have a piece of software that you're executing, as opposed to get the behavior, as opposed to a model of the software executing, and which would definitely be simulation.
So I think it's time to close. I want to make two quick announcements. First, we're getting quite full, but we still have a few places left. If you've received an invitation or want an invitation, if you're from industry or government, to our TCIPG Industry Government Workshop that will be on October 30 and 31. Our whole hotel block expires in the next couple days, so please register and make your hotel reservations. And we will have a speaker from Idaho National Lab next week at our First Friday webinar. Next month, first Friday of November. And thank you very much, David. In addition to all of us here, we had, I think, 27 other sites that tuned in today. So we really appreciate an excellent talk.